In chemical engineering, the math often assumes perfect, isothermal conditions. But in reality, ignoring heat generation leads to disaster. When thermal energy exceeds conduction limits, reactors can suffer catastrophic failures, resulting in significant human and financial costs. This video explores the dangerous gap between theoretical models and physical reality. Consider the anatomy of a batch reactor. Math often assumes perfect, smooth walls, with high heat transfer efficiency. In reality, polymer fouling acts like a thermal blanket, dropping efficiency by 40%. Modern mitigation uses machine learning to predict this fouling and trigger automated cleaning before degradation occurs. Scaling a reactor is like managing a thermal pressure cooker. Turbulence, eddy diffusion, and conduction interact in complex ways. While standard numbers assume perfect conditions, real-world hotspots cause microboiling, creating vapor blankets that choke heat transfer. AI failsafes now process infrared camera feeds to detect these micro-hotspots before they trigger a runaway reaction. The evolution of thermal control has moved from manual, high-risk methods to advanced AI systems. Early industrial eras relied on reactive feedback, which often failed to handle nonlinear reactions. Today, Industry 4.0 uses model predictive control to anticipate thermal lag and adjust coolant flows preemptively, stabilizing the process. The map is not the territory. Theoretical mass and energy balances often assume perfect heat exchange. However, physical reality, like pressure drops in valves, can lead to two-phase flow nightmares that destroy heat transfer efficiency. AI-driven schematic auditing now scans for these contradictions before any equipment is ever built. Thermal expansion presents another trap. A design might have a nominal 5 mm clearance, but at 250 degrees Celsius, the central shaft elongates, collapsing that gap to just 1 mm. This can cause the impeller to seize mid-reaction. AI Generative Design optimizes geometry to ensure uniform thermal distribution while maintaining structural integrity. The Arrhenius curve illustrates the exponential risk of thermal runaway. Heat removal is often modeled as a linear process, but heat generation is exponential. When local temperature spikes occur, simple models severely underpredict the reaction rate. Physics-informed neural networks now solve these equations in real time to track spatial anomalies. Traditional computational fluid dynamics can take weeks to solve a single simulation. AI surrogate models, trained on thousands of high-fidelity simulations, can now predict thermal stress in milliseconds. If real-time sensors detect a deviation of more than 2%, the system triggers a high-fidelity resolve to ensure safety. The digital twin bridges the gap between the blueprint and the physical asset. By using IoT telemetry and sensor fusion, the system can identify when sensors drift due to fouling. This allows for constant recalibration, ensuring the digital model remains a true representation of the physical reactor. Dynamic AI control must account for mechanical realities, such as valve stiction, which can cause significant thermal lag. Reinforcement learning agents simulate millions of batches to map this inertia. For ultimate safety, hardwired, independent systems override the AI if safety bounds are breached. Manufacturing tolerances are often hidden entropy traps. Microporosity in welds can create tiny crevices where reagents stagnate, causing invisible thermal hotspots. Automated ultrasonic testing and computer vision are now used to scan every weld bead, flagging defects before assembly begins. When models fail, a matrix of mitigation is required. From fouling-induced heat transfer drops to valve stiction and nozzle clogging, these issues are predictable. By incorporating these realities into predictive maintenance and AI reward functions, we can effectively manage the risks that traditional models ignore. Generative design allows us to rethink hardware entirely, like the alien impeller. By optimizing purely for fluid dynamics and heat transfer while enforcing strict manufacturing constraints, we can create topologies that eliminate dead zones and significantly boost performance. Looking toward the future, the batch reactor is just a training ground. Our goal is to move from macro mixing to precise molecular manufacturing. Quantum machine learning will be essential to predict reaction pathways in real time, allowing for self-correcting atomic assembly in the face of thermal noise. Ultimately, physical reality will always introduce chaos. We cannot defeat entropy. We can only design systems that manage it. Through first principles math, brutal engineering, and advanced AI, we build fault-tolerant systems to contain the chaos. We hold the line.